What specific problem does Tokenformer aim to solve in the context of existing transformer architectures, particularly regarding token parameter interactions?
Tokenformer aims to address the scalability limitations of existing transformer architectures, particularly concerning token parameter interactions, which are traditionally handled through prescribed linear projections. This conventional approach necessitates retraining the entire model from scratch whenever the model size is increased, leading to excessive resource consumption and inefficiency. By introducing a fully attention-driven architecture, Tokenformer unifies token-token and token parameter interactions, allowing for a flexible and scalable design that can incrementally add new key-value parameter pairs without disrupting the existing model. This innovative token parameter attention layer enhances the model's scalability and enables the reuse of pre-trained models, significantly reducing the training burden while maintaining competitive performance. Thus, Tokenformer effectively mitigates the high computational overheads associated with scaling transformer models.
How does the proposed Tokenformer architecture work? Please illustrate step by step, focusing on the token parameter attention layer and its integration with the overall model architecture.
The proposed Tokenformer architecture operates by unifying token-token and token parameter interactions through a novel token parameter attention layer. First, it introduces two sets of learnable parameter tokens, which serve as keys and values, allowing the model to dynamically interact with a variable number of parameters independent of the input and output dimensions. In the potential layer, input tokens are treated as queries, while the parameter tokens are utilized to compute attention scores, enabling efficient scaling of model parameters by appending new key-value pairs without altering the existing architecture. This design preserves the integrity of pre-trained models, facilitating incremental scaling and reducing training costs significantly. Overall, the Tokenformer architecture maintains a fully attention-driven framework, where all computations, including those traditionally handled by linear projections, are executed through attention mechanisms, enhancing flexibility and performance across various tasks.
Can you provide a simple example that demonstrates the inner workings of the Tokenformer algorithm, particularly how input tokens interact with parameter tokens?
The Tokenformer algorithm operates by utilizing a novel token parameter attention layer, which allows input tokens to interact with parameter tokens through a cross-attention mechanism. For instance, consider a scenario where we have input tokens represented as I in math bb r caret t times d underscore 1, and parameter tokens as k underscore p in math bb r caret n times d underscore 1 keys, and v underscore p in math bb r caret n times d underscore 2 values. In this setup, the input tokens serve as queries, while the parameter tokens act as keys and values. The output is computed by first deriving attention scores based on the similarity between the input tokens and the parameter keys, followed by applying a modified softmax operation to obtain normalized weights. These weights are then used to compute the output by aggregating the parameter values, effectively allowing the model to dynamically adjust its computations based on the input, while maintaining the flexibility to scale the number of parameter tokens independently of the input and output dimensions. This design enables efficient reuse of pre-trained models and facilitates incremental scaling, as new parameter tokens can be added without disrupting the existing model's learned distribution.
What are the primary theoretical or practical benefits of using Tokenformer compared to traditional transformer models, especially concerning training costs and scalability?
The primary theoretical and practical benefits of using Tokenformer compared to traditional transformer models lie in its enhanced scalability and significantly reduced training costs. Tokenformer employs a novel token parameter attention layer that unifies token-token and token parameter interactions entirely through attention mechanisms, allowing for a flexible and scalable architecture. This design enables incremental scaling of model parameters by adding new key-value parameter pairs without necessitating retraining from scratch, which is a major limitation in traditional transformers that rely on fixed linear projections. As demonstrated, Tokenformer can scale from 124M to 1.4B parameters while achieving performance comparable to training from scratch, but with over half the training cost. This efficiency is further highlighted by the model's ability to maintain the integrity of pre-trained knowledge, facilitating faster convergence and making it a more resource-effective solution for developing large-scale models.
How was Tokenformer validated or tested in the experiments? Describe the datasets, metrics used, and the results compared to the baseline transformer model.
Tokenformer was validated through a series of experiments using the Open Web Text Corpus, which consists of textual data from Reddit shared documents and the piled dataset for language modeling tasks. The evaluation metrics included perplexity for pre-training performance and zero-shot performance measures across various downstream tasks. In comparison to a baseline transformer model trained from scratch, Tokenformer demonstrated competitive performance, achieving a test perplexity of 11.77 at the 1.4B parameter level, while the baseline achieved 11.63 but required 3 times the training cost. Additionally, Tokenformer was shown to require only 1/10 of the computational budget compared to the baseline transformer for similar performance, highlighting its efficiency and scalability. The experiments confirmed that Tokenformer effectively maintained performance while significantly reducing training costs, validating its innovative architecture.
What limitations or drawbacks were observed in the Tokenformer architecture, particularly in relation to its incremental scaling and parameter interactions?
The Tokenformer architecture, while innovative, does have some limitations regarding its incremental scaling and parameter interactions. One notable drawback is that, despite its ability to scale parameters incrementally without retraining from scratch, the architecture still relies on the attention mechanism, which can introduce computational overheads, particularly as the number of parameter tokens increases. Additionally, while the potential layer enhances flexibility, it may not fully eliminate the complexities associated with managing interactions between a growing number of tokens, potentially leading to inefficiencies in very large models. Furthermore, the reliance on the JLU function for improved gradient stability, while beneficial, may not universally address all training instabilities, indicating that further optimization could be necessary. Lastly, the model's performance, although competitive, still requires careful tuning and validation to ensure that it maintains efficiency and effectiveness across diverse tasks and datasets.